Okay. Okay. So can you hear me? Oh, okay, great. So yeah, I'm connecting from hotel. So if there's the one important thing before I begin the talk is that if there's a connection problem, please let me know or write in chat, etc. So that because otherwise you don't hear what I'm saying. Okay. So well, first of all, let me thank the organizers for giving me opportunity to present this talk. So this is an online talk, but I'm coming to Cambridge in a few weeks, and I'm excited about it, and I'm going to see many of you there. So what I'm going to talk about today is based on collaboration with the four IPMA alumni listed here, me, Ashwin Kumar, Matthew Doderson, Apiram Kidambi, and Jacob Reedham. And interestingly, all of these people went to Europe. I think Apiram might be there, but let's see. So in fact, all of them are in Europe, which are closer to you. So you might have some opportunity to meet some of them. And the paper-wise, there was one paper which published in 2021, and this was a result of our effort during the pandemic. So we wanted to do something new, and then we started the reading club, etc., which culminated in this paper. And afterwards, with Ashwin and Jacob, we put out a paper a couple of months ago about the emergence of the global symmetries in this holography. And then we are now, like now, we are almost finishing the paper, which will hopefully to appear. Well, not next week maybe, but hopefully very soon. And what I'm going to talk about is based on these papers. Okay, so let me get started. So what are the main themes of this topic, of this talk? Well, there are at least two themes, which are both related to the main themes of this workshop. One is the interaction in number theory and physics. So to this audience, this requires no justification, but at least in the context of my talk, what's interesting is that there is a number theory concept. And initially I thought that the number theory concept just appears, and I just want to take advantage of that and then just grab the formula or something like that. But I begin to realize that many of the structures which exist in number theory literature has some more direct meaning in the physics. And that's why I'm getting more excited about the story. And the second, there is an ongoing discussion about how to think about ensemble averages in holography. So what is meant by the ensemble average? Well, it's average over ensemble, obviously. But what is meant by that is the average over a class of quantum field theories, which in my case is conformal field theories. So usually in conformal field theories, there is a set of parameters. So you can deform the conformal field theory. There's a conformal set space of marginal deformations and a conformal manifold. And so this is the ensemble, what I call the ensemble. And different points on this ensemble are in the standard sense different series because it's marginally deformed. And so usually they're considered to be different series. But nevertheless, you can be very bold and try to take an average over the class of series, and then go and get something. And this idea of ensemble averaging is getting popular these days, especially after the work of Sal-Schenker and Stanford. And some people tend to, it seems that people believe that's fundamental for holography, etc. The debate is going on, but at least for the purposes of my talk, it gives a useful, interesting way to extract some sort of a coarse graining operation, which extracts the information in a nice way. And that's where the contact with number theory comes in. And I should also say that since this is a conference about a quantum black hole, well, I'm not going to see Leria black hole, but we're going to encounter the BTZ black hole because I'm going to discuss the ADS3 gravity. Okay, so these are the main themes of the topic. And in this talk, I'm not going to list in fact, I'm going to omit most of the references. I really apologize for the experts in the audience. Well, so for references, please refer to a paper. But let's see, but at least I should refer to at least the two papers, which was the initial inspiration for us. And one is this group, Tob Hart et al., and another is the Maroni Witten. And this paper was really the inspiration for us. And what they did is they discussed the ensemble averages of this Narain series. So the standard Narain series. And we started by trying to generalize the discussion. And okay, so what do you mean by generalization? Well, the Narain series are associated with even self-dual lattice. So that's as in standard string theory textbook. And if you read a string theory textbook, they say that the lattice should be even and self-dual. That's it. However, we realized that you can actually discuss, at least in this particular context, discuss more general lattice, which is still even, but not necessarily self-dual. And you can associate a class of series to these lattices, and then we can discuss the ensemble average. So it is some generalization, and initially I thought that this is a small generalization, but it turns out that there are a lot of very rich structures which exist only when you consider these more generalized Narain series. And in fact, most of the discussions in our second, third paper, etc., are based on the novel features which exist in generalized Narain series. So in this talk, let me start by describing this generalized Narain series. And initially, I thought that the generalized Narain series, these are well known in the literature, but I tried to look into literature myself, and there are surprisingly very little discussion of these series. And perhaps one of the reasons is that these series are not modular invariant. So these series are not modular invariant. So in some definition, it's not a conformal field series if you include a modular invariance. However, these are still a well-defined series. For example, the sphere, and even the torus, it has just it has a well-defined partition function. It just transforms non-trivially under the modular transformations, and these are actually very not much is fit. These series fit in very nicely into the ensemble average, as we'll see. Okay, so let me try to describe the series, and then so usually the good way is to remember the simplest case, and in this case I start with the S1 Narain series, as in string theory textbook. Okay, so in this case there is a Narain lattice, which is the momentum lattice, and then these are labeled by two integers, n, which is the momentum number, and then w is the winding number, and then left movers and right movers, there's a momentum. And in particular, there's a S1 with the radius r. So there's this parameter, which is this r. Now, there is a nice quadratic form, which is PL squared minus PR squared. It turns out there are a lot of cancellations, and you get 2NW, which is an integer, and it's even. So, and then this you call the even quadratic form. So even quadratic form, in this case, is simply 2NW. For a set of integers, no, in this case, not integer, just a set of integer NW. And the Hamiltonian is simply PL squared plus PR squared, and you get this expression. And Hamiltonian depends on the radius, whereas the quadratic form or the lattice of quadratic form itself doesn't depend on the radius r. So this r parameter is the modular space ensemble, if you like, in this context. And r runs from 0 to infinity, but there is a famous t-duality, which sends r to 1/2r, and so you can try to it's enough to consider only half of the modular space from r equals to half to all the way to infinity, because the other part between 0 and half are related to the other one by a t-duality. So, okay, so the basic building block from here is that there is a quadratic form, and which is modular independent, and even quadratic integer form. And then there is this Hamiltonian, which depends on the moduli. So, okay, so then what is the general version of this Narain series, which is somewhat similar? So again, we start with the integer quadratic form. And previously in the S1 case, it was signature 1, 1. But here, more general one with the signature P, Q. And I'm going to impose the condition that it's even quadratic form. So if you take integer values, and then it's always returns the even number. Now, in addition to this discrete data, there's also a modular parameter, which specifies the decomposition of this quadratic form into left and right movers. In other words, it specifies the decomposition Q into PR squared minus PR squared, so it specifies into left movers and right movers. And the Hamiltonian is simply given by the sum. Okay, so I think, okay, so you don't see the cursor now. Okay, so I don't know how to show the cursor, sorry. Let's see. Oh, okay, I don't know how to show it. Okay, I guess it's fine. Let's see, could I show the cursor? No. Okay, yeah, I can live with that. So then let's see. So the Hamiltonian is dependent on the moduli, And previously, it was just R, which is a single parameter. But in general, there are multiple parameters. In fact, P times Q parameters in general. And then that specifies a point in the moduli space, CFT moduli space, which is this MQ. And that's essentially very similar to the usual Narain moduli. Specify OP plus Q, and then you have to quotient by OP times OQ, which rotates each of the left and right movers. And in addition, there is a discrete group, which is a T-duality group, which is an integer set of orthogonal transformations compatible with the quadratic form. So hopefully this is clear. So this is but the important thing is that I haven't again imposed the modular invariance. Now, okay, so here we want to associate some expression, concrete number theoretic expressions here, and the natural candidate is the theta functions. So so this is similar to usual theta functions, but somewhat more general, associated with the quadratic form Q. And it depends on tau and tau bar, or tau 1 plus tau 2, real and imaginary part. And tau 1 and tau 2 appears in the exponent with coefficient Q and H, respectively. Now, the H depends on the point in the moduli, as I described before, and then small m. So I'm going to write the small m as one of the arguments for the theta function. Well, if you like, you can write down the expression as a Q2 power momentum. So that's the second line. So this is a theta function, generalizing the more standard definition of Jacobi theta. And well, let me say that the tau and tau bar are the moduli of the torus. So we have the partition function of the torus, and then this tau is the moduli of the torus, whereas the m is the moduli of parameter for the CFT moduli space, which sometimes is almost like a torus, but it's a different different parameters. So tau and m are different, so that's important for what torus. Okay, now for the later purposes, it actually turns out to be a little bit useful to generalize the theta function a little bit by incorporating this parameter alpha, which appears in one of the lower indices. And it just shifts this sum. So when you sum over L, which is over the lattice, you just shift the lattice by this parameter alpha. And everything else is the same. Where alpha is an element of the lambda star divided by lambda. So lambda star is a set of points such that when you take an inner product with the lambda, it becomes an integer. And so lambda star contains lambda, but it can be in general larger, and the quotient is called a discriminant group. So alpha is the element of lambda star over lambda, and that appears extra data in the definition of the theta function. And one of the technical reasons why this is useful is that it appears natural in the modular transformation. So so the theta function I defined transforms non-trivially under the modular transformation. So let's say if you take a T transformation, it's diagonal. There is a phase exponential I pi q of alpha comma alpha. So it's a phase, and it doesn't change the index alpha. Whereas if you do the S transformation, you're going to get a little bit more complicated transformation. And there are many factors there, but what's important is that you have a sum over all the betas, all the discriminants. And on the right-hand side, you have the theta function, which depends on beta. So in other words, even if you start from the theta function with alpha equal to 0, then if you do the modular transformation, then you get the theta beta for all the different values of beta inside the discriminant. So these are like these theta functions with different values of discriminant. These are like a basis of vector spaces, and S and T transformations act non-trivially on them. Now, if you want to discuss the honest torus partition function of the CFT, you would rather divide this by product of eta functions. So with the power P and Q. So P and Qs are signatures of quadratic form. And if you like, it's more like a central charge, left movers, moving, and right moving central charge. And the ratio I denoted by Z, which is the partition function. Now, since we already know the modular transformation of the theta functions, and you already also know the modular transformation of the eta functions. You also know the modular transformation of this partition function z, which is immediate to right, and it takes a little bit simpler form than the previous theta function. It still transforms essentially the same way. T acts by multiplication by phase. S acts like a Fourier transformation, discrete analog of the Fourier transformation, in the sense that you sum over beta, and then the coefficient sitting in front is exponential minus 2 pi I, and the pairing between alpha and beta as specified by the quadratic form. And so this is like the type of representation which appears in quantum mechanics. Yes.
Yeah, sorry to interrupt. For the case of S1 at radius r, what does alpha take values in? Like, how many different alphas are there?
Well, yeah, in that case, there's single value of alpha, which is alpha equal to 0.
Okay, so there there's nothing interesting.
Yeah, right. There's nothing interesting in that case.
Well, what about for two? Like for central charge 2?
Central charge 2. Well, you have to specify the Q itself. So when Q is not the self-dual, then there is this non-trivial beta and alpha. So beta and alpha, they take values in the discriminant, lambda star over lambda. Sometimes lambda star equals lambda, which is the self-duality condition. And in these are in almost all the string theory literature, lambda star is equal to lambda. And because of that, alpha is 0.
Okay, thanks.
Yeah. So in fact, because of that, you usually don't see this type of structure in string theory literature. But it's but it's some natural ingredient here, as you see in this modular transformation already. And for example, the number of, so you can ask the question how many alphas there are. Well, it appears there's a square root of determinant Q appears there. Indeed, the number of alpha or the number of elements in the discriminant group is the same as it's given by the determinant of Q, absolute value of determinant Q. So you can easily guess, compute how many such alpha betas there are. Okay, so this is the almost purely mathematical discussion. Well, you can ask the question how to construct the CFTs, etc., from vertex operators, etc. In the forthcoming paper, we are a little bit more explicit, but you can imagine that you can generalize many of the ingredients of the Narain series to this setup. Okay, and then let's try to discuss the ensemble average. For this, as I said, this is really inspired by the two papers, but we try to generalize it to this general quadratic form case, and so that's what we did. So let's discuss the ensemble average. Well, first of all, we need to specify what we mean by ensemble average. The ensemble itself was clear. There is a Narain this double coset. Okay, so let me go back. Sorry for scrolling down. So there's this CFT modular space MQ. So that's basically the modular space over which we integrate. And it's described by a coset. There's a discrete application, but it's OP plus Q, quotient of OP plus Q. So by definition, there's OP plus Q symmetry. And there's a nice metric which is compatible with the symmetry. So there's a canonical metric coming from the fact it's a symmetric space. It's like a hard measure. And then that's the metric we are going to use. In a more physical language, there's a Zamolodchikov metric determined from the two-point function, and that's the one you're going to use. Now, there's one subtlety, which is that if you want to average the theta Q alpha with non-zero alpha, the element of the discriminant group, you have to change the modular space a little bit. So previously, you divide by the whole T-duality group. That was the definition of MQ. But it turns out that if you have non-trivial alpha, not all the T-duality group preserves alpha. So instead of dividing by the whole T-duality group, you have to divide by the T-duality subgroup of the T-duality group, which preserves alpha. And that I denote by MQ alpha. Okay, but that's actually a little bit subtlety, so you don't need to worry too much about it. And in any case, there is a Narain-type modular space, and you're going to do the ensemble average of the theta function of that expression. And then the question is what that is. And fortunately for us, in fact, the papers, the two papers I mentioned by Hartman et al. And also Maroni et al. So these papers noticed that there is they can do the integral, and that was thanks to the formula by Jige and Bale. So we call it the Jige-Bale formula. Yeah, so their analysis was self-dual Q again, but if you look at the paper, they actually didn't impose the condition Q is self-dual. And then so what is the result? Well, the result is some non-holomorphic Eisenstein series, which I denote by EQ alpha. And this formula is a very beautiful formula. I became increasingly fascinated by it. And in fact, I somehow became interested in the Carl Ziegler himself. So this formula was proven by Carl Ziegler, and Andrew Bale, his cleverness, he formulated in a much more fancy way in terms of adelic integrals, etc. But for our purposes, what Ziegler did is more for the most part sufficient. And in fact, Carl Ziegler was seems to be a very genius, really a genius, and he has done a lot of interesting stuff in analytic number theory, and even celestial mechanics, etc. And I became fascinated by this formula because many of the ingredients, if you look at it from today's viewpoint, kind of predicts what might happen in Chern-Simon theory, for example, decades later. And in fact, I digged in, and there are a lot of people say a lot of good things about Carl Ziegler. And well, sorry, I'm digressing too much, but this is probably what you haven't seen because it's a little. It was a comment by Taniyama, who was in Japanese, and he says that while Bale is a genius in putting together existing theories, he lacks true originalities. Wow, that's a harsh comment, but then he cannot match the creativity of Ziegler. So that's what the Taniyama said. And so anyway, so Carl Ziegler is an amazing guy, and then this is his formula. And of course, let's see, in order to understand this formula, you need to know what this right-hand side is. So you need a separate definition to make sense of this formula. And one definition is given by this expression. Okay, so it's typically called a Poincare sum. Okay, so the left-hand side EQ alpha, it actually depends on tau and tau bar. It's a non-holomorphic Eisenstein series. So I really should write tau and tau bar. But sometimes it's a little bit annoying to keep writing tau and tau bar. So sometimes I just write tau in the notation. And on the right-hand side, there is a sum, infinite sum over a set of integers, C and D, which are co-prime, and C is positive. And then this specifies an element of actually PSL instead of SL. Sorry, there was a typo. So if you have a co-prime integer, CD, then you can find you can take that as two entries of the element of PSL to Z, and then fill in the rest. Well, and then the rest, there are ambiguities, but that ambiguity, so you have to quotient by that ambiguity if you want to specify, if you talk about CD only. And that specifies the group, I would say PSL to Z over the set of integers. So which is typically called gamma infinity. Okay, anyway, there is a, if you like, you can simply think of it as sum of a CD. And what's inside? Well, first of all, there is a simple formula like a theta plus D over 2, Q over 2, etc. So the denominator depends only on the tau bar and PQ. So the signature of capital Q. And the information of the quadratic form capital Q enters into the formula above in this gamma factor. And then the second line, you have this gamma capital Q comma alpha, and it's given by this impressive formula. It's a sum over lattice divided by C times lambda, et cetera, et cetera. So it's some sort of a Gauss sum, some version of the Gauss sum, and interesting number theory quantity. And indeed, again, so this factor gamma essentially appears only when we consider this non-self-dual case, non-self-dual Q. So the previous two papers, which was the inspiration for us, didn't have this factor. It was simply 1. And yeah, so this is the one definition of this Eisenstein series, and then the statement is that matches the ensemble average on the left-hand side. So that's a Ziegler-Bale formula. Now, you can try to get the intuition as to where this formula comes from. Well, the important thing is that I already called this Eisenstein series, and which is indication of the fact that this is a modular form. So indeed, you can take this and then study the modular transformation, etc., directly from this definition. Well, but let's see. And then it turns out that this is a modular form with respect to some congruent subgroup. And in fact, that's expected from the this left-hand side too. So right-hand side is, I said, is a modular form. What about the left-hand side? Well, left-hand side is integral of the theta function. And we already see the modular transformation of the theta function. So it's a little bit smaller, but I just copied what I showed before. This is the modular transformation for the theta function. Theta capital Q comma alpha. And then what's the important thing is that there are a lot of factors, exponential I by Q, etc., or tau bar, etc. But none of these factors which appears in front depend on the modular M. So these are completely independent modular. So when you do the ensemble average, these factors are not at all affected. So you can easily discuss the ensemble average and then the modular transformation of the ensemble average quantity. So the ensemble average I denote by this bracket denoted by alpha in the below. So this ensemble average quantities, they have exactly the same modular transformation properties as before. And it turns out that there are a lot of factors hanging around here. And because of that, it's not quite the modular form in the standard sense. But if you take some subgroup, which is gamma L, some congruent subgroup related to Z, you can show that all these factors go away and it becomes a standard modular form. Well, if you care about this, what is gamma L? So L is the integer called the level of the quadratic form. And it's the smallest integer such that L times Q inverse becomes integral. So Q is an integral quadratic form, even, yeah, it's actually even, but Q inverse is not necessarily in integrals, and you have to multiply by some integer to get an integral form, and that's known as a level. Okay, but that's not terribly important for what follows. So you can show that it's a modular form with some congruent subgroup. And if you go back to the definition of the Eisenstein series, which I copied here, you can see that the Poincare sum is meant to reproduce the modular transformation on the right-hand side. Modular transformation above, which in this slide above. So, for example, if you have a downstairs, you have a sum over CD, co-prime, C prime, etc. So that's a Poincare sum. And each has a factor of C tau plus D, C tau bar plus D. And in particular, it has a cusp that tau goes to minus D over C. A set of points. And these are related to I infinity by modular transformation. And that should be compatible with what you find above. So above, you know the modular transformation. The modular transformation sends I infinity to minus D over C, set of rationals. So once you know the modular transformation at infinity, then when combined with the modular transformation, then, once you know the asymptotic as I infinity, then by combining that with the modular transformation, you know the asymptotic behavior at all the rational points. And that should be compatible with the gamma, which you find here. In other words, this gamma is essentially determined from the modular transformation properties above. So that's how these two things are compatible. In fact, you can make the argument a little bit into essentially the proof. So, so this is not exactly how Ziegel proved it. Ziegel was, it seems that as far as I know, it was really computing it somewhat more down to earth in a sense. But you can make it what I said before as a kind of a proof. So you have the ensemble average and the Eisenstein series defined as a Poincare sum, and take a difference, which I denote by F. And one thing I can show is that they behave the same way under the modular group. So they are both non-homomorphic modular formed with respect to some congruent subgroup, gamma L. And since they have the same modular transformation property and the same asymptotics at one of the cusps, I infinity, the cusps, at the behavior at the cusps, all the singular behavior cancel out, and such that F becomes a regular function, and then hence becomes square integrable. So F is a nice square integrable function, and moreover, you can show that it satisfies some differential equation. Where box, I forgot to write on the box, but it's some Laplacian on the upper half plane. And if you combine these facts, you can show that F is 0, and hence the ensemble average is the Eisenstein series. So this is the proof, and let's see. So perhaps you might not all of you are interested in the proof, etc. But the point is that you can. This is a very sophisticated result, but you can try to kind of sink yourself in and try to prove it in a relatively down-to-earth way. So the expression of the Eisenstein series, there was a gamma, which is a complex expression. But if you think about the meaning, then you can more or less determine the gamma yourself. And that's very important because I'm not coming to the holographic interpretation of the theory. So, okay, so here beforehand, we just take the CFT and then did the ensemble average. Everything is the CFT side. But if you might be interested in what happens to the bulk. And mathematically, the target is very clear, the theta functions and the Eisenstein series, and how to reproduce that from some three-dimensional theory. And the answer is that essentially it's a abelian Chern-Simons theory in the bulk. In the sense, I can try to be a little bit more specific, but it's essentially abelian Chern-Simons theory. And then, well, you can even discuss the theory before the ensemble average. And it turns out that's abelian Maxwell Chern-Simons theory. Okay, what I mean by that is, in addition to Chern-Simons term, we have a Maxwell term, the standard kinetic term. F mu nu, F mu nu. Yeah, so, well, I forgot to say that in the abelian Chern-Simons theory, you have P plus Q U1s, and there's a level which is sitting in front, and the level is determined from the quadratic form itself, Qij. Well, let's see. So you might suspect that let's see, even if you add the Maxwell term to Chern-Simons, it's completely irrelevant. That's what we usually say. Well, because the Maxwell term is dimension 4, but which is dominated by Chern-Simons term, which is true. The only subtlety is that if you add the Maxwell term, it changes the quantization condition of the gauge field. So if you keep track of what happens to the lattice, it modifies the structure of the lattice of what happens and to the electromagnetic charges, and that sounds similar to what happens to the Narain theory. Okay, so let's see. But let me try to explain this a little bit more detail, especially after the statement that the abelian Chern-Simons series is due to the theory after the ensemble average. Well, first of all, so this is the theory. So this is again just the Chern-Simons term. Oh, okay, in this convention it should be 1/8 pi, I guess. But in any case, it's a standard abelian Chern-Simons theory. Well, interestingly, these are also theories which, for example, condensed matter people discussed in connection with the topological phases. So at least the theory defined from the quadratic form, so it seems to be a good starting point. Now, you might immediately be a little bit suspicious that it has a Chern-Simons term. Usually you don't have a Chern-Simons term in the bulk, but there are some situations people consider in holography where there's a Chern-Simons term, and this is similar to that. So one of the complaints you might have about the Narain theory on the boundary is that it's not modular invariant. So if you like, there is a gravitational anomaly, but that is matched by the Chern-Simons term in the bulk. Now, okay, so now the third point is that you have to reproduce the Poincare sum, or we are going to do the quantum gravity, so we have to consider sum of the geometries. And the Chern-Simons theory itself doesn't do the sum of geometry. So a little bit more precise statement is that you have a sum of exotic theory of gravity, and which means that you have sum of geometries. But once you pick up a specific geometry, which in this case is SL to Z black holes, then the partition function there is given by the Chern-Simons theory on the same manifold. So it's like a collection of Chern-Simons theory on different manifolds. And the geometry in questions is familiar for people interested in number theory, etc., which is the SL to Z orbit, and more physically, that's the class of SL to Z black holes, which appears, for example, in the black hole fairy tale expansion. Okay, I'm going to comment further on this later in one slide or so. Okay, so this is data for Q. But let's see, but you might say that, for example, okay, so let's first think about it. So Eisenstein series, EQ alpha, there was extra level, which is alpha. Okay, what is alpha? Well, it turns out that alpha specifies the anion of the Chern-Simons series. Okay, so what is meant by that? So first of all, the Eisenstein series, okay, so it was a partition function on the torus, on the boundary. But now we are doing the holography. So what we do is that we are going to do the three-dimensional geometry whose boundary is a torus. So it's like a wave function of the three-dimensional series on torus. And the theory we are talking about is simply abelian Chern-Simons series. And in abelian Chern-Simons, well, abelian not, in fact, in Chern-Simons series, we already know what type of modular space, Hilbert space we expect on the T2. And so we have, well, in the usual case, we have a conformal block, etc. And then there's, it's a final dimensional space. And the basis of that space, Hilbert space, is determined, labeled by an anion. And that means too that we are considering here in this picture, we have a solid torus. And then we're going to include a Wilson line inside. And if you do the path integral with the Wilson line included, that gives another element of the boundary torus, Hilbert space. And what are the choices of the anions we can include? Well, first of all, you have to consider all the possible charges. But then there is a gauge equivalence class. And that's how you get a final dimension Hilbert space. For example, if you have a U1 with level K, I think there are K choices. And what is the discriminant group, lambda star over lambda, is just a fancy generalization of that. So the anions specify the basis. And yeah, okay, so this the function I comment on later. Now, and once you know that we have a theory of anions, you begin to, the modular transformation I mentioned before, beginning to make sense. So here, I copied the modular transformation formula, which I showed before. Now, there is an interesting factor, exponential I pi q alpha alpha for T transformation, and for S transformation, exponential minus 2 pi I q alpha beta, etc. So there is some factor, exponential factor, sitting in front. That was the modular transformation of the theta function approach with the element of the discriminant group, which is alpha, beta, etc. Now, in the Chern-Simons language, the meaning is that you have these anions labeled by the Wilson line, and then the question is that how does the modular T and S transformations act on the abelian anions? And there is already essentially a formula saying that the T transformation is diagonal with the so-called topological spin of the anion, which is, in fact, it turns out it's determined by this formula, I pi q of alpha comma alpha. And there is similarly a formula for S transformation, which is determined by this pairing between alpha and beta with respect to the quadratic form. And this shows that essentially the braiding between two anions. You have two anions, you can rotate with each other. I should have a picture there. So if you have two anions, you can rotate with each other. That's a braiding of the anions. And that gives the extra phase, and that is given by this formula. And in fact, usually in the TQFT, if it's a non-abelian anions, you need to specify more complicated data like a fusion, etc. But it turns out for the abelian group, the fusion ring structure is so simple. So essentially, everything is encoded in the choice of the quadratic form and associated S and T matrices. So S and T matrix is here, but that determines from the quadratic form. Simply the modular, so the alphas, discriminants are anions, and the modular transformation is determined by the braiding structure and the topological spin of the anions. So by hindsight, I really computed these factors, etc. by Poissonry summation, etc. But once you understand the bulk, you don't even need to compute it. It's kind of obvious. Now we have we can come back to the Eisenstein series itself. We have a sum of a sum, Poincare sum. Now, so the Poincare sum, so it's a sum of a CD comma 1, coprime 6. So this specifies element of SL to Z mod gamma infinity. And you can think of this as a sum over SL to Z black hole. So it's just a solid torus, and it's always a solid torus with boundaries torus. But you can choose which directions is the torus is the time direction. And if you apply the SL to Z transformation, you get a different thing. Some are ADS, BTZ, and many other geometries. And the sum represents the sum over black hole of these geometries. And at least these are the smooth geometries in 3D gravity, which is compatible with the boundary condition of the torus. And then there was a mysterious factor, which is gamma. What I said before, okay, maybe the explanation was a little bit murky, was that this gamma was related to modular transformation properties. And you can make it even more explicit here. So what is gamma? It turns out the gamma is a partition function of the Chern-Simons series on the length space. So if you have C and D, what I said before is that you can promote it to a matrix of PSL to Z. And then once you have the matrix, there is a corresponding operator. So that's the element of PSL to Z, and that acts on the Hilbert space on H2. On the Hilbert space of the T2, the two-dimensional torus, which is the boundary of the solid torus. Now, this length space, the gamma is obtained by gluing two solid tori together with an element with identification given by this PSL to Z matrix. And then the end result is that you're going to get the length space. And here, well, you have a gamma Q alpha, which means that you have a Wilson line. I forgot to draw it, but we have a Wilson line in one of the solid tori, but not the other one. So that's how you get. So in other words, gamma Q alpha is simply the matrix element of the modular matrices in the acting on the space of anyons. So that is the interpretation of the whole structure. Now, okay, so since I seem to have 15 minutes or so, I hope people find. So let's see. Are there any questions at this point? Okay. Yes. Yes. Yeah, it was really gamma. Yes. So it means that. Well, sorry, index. Yeah, let's see. Oh, sorry, I shouldn't stop sharing. Yeah, let's see. Okay, so I could go back there. What was the? Sorry, I need to remember for what. Was it here? Oh, sorry. Okay, I guess I. Oh, here. Yes. Yeah. Let's see. Yeah, upstream later inversion. Okay, that's that I don't. Yeah, okay, that I don't remember now. Yeah, but this is not gamma 0. This is really gamma L. So you have the both off diagonal elements, not just if you write ABCD, not just B, but both B and C are 0. Yes, that's right. So yeah, if I, for example, if you take just the gamma naught L, for example, then that simplifies some of the modular transformation property for T transformation. So you need to consider T to L, not the T, for example. That simplifies the formula. Indeed, that eliminates some of those things. But to simplify the S transformation or some other generators, you need to specialize more, and that's why you need to have a gamma L. And in fact, the fact that it's all the factors simplify for gamma L, it's a non-trivial result. I think originally we found it in the paper by Oda, which in turn comes from the paper by Sintani, which discussed the things. So in a forthcoming paper, we might have appendix on that in the to show that explicitly that it's a gamma L, not gamma naught L, for example. Okay, yeah, I never thought about that. Yes, yes. Okay, then can I proceed? Okay, then let's proceed. Let's see. So then let's come to the little bit more conceptual part. So here is the structure, and now there is you can also, this is a lot of sophisticated setup involving very interesting number series stuff. So there should be interesting physics too as well. And then you can ask the question of the global symmetry, for example. Now, one of the conjectures in quantum gravity is that there are no exact global symmetries. That's people sometimes call one of the swampland conjectures, etc. And that seems very plausible. Now, let me quickly point out that the abelian chance symmetry we are talking about do have global symmetries, 0 form, 1 form, etc. So they do have global symmetries. And it's a little bit surprising in that respect. But well, let's see. At least it's not there is no contradiction here, because when people say that there are no exact global symmetries, etc., people clearly have in mind the standard Einstein gravity and the black holes there, etc. Here we have more exotic theory described by Chern-Simons theory, etc. So the argument doesn't apply. So there's no contradiction. So which is fine, but okay, but if that's the case, okay, so if there's this is a rare situation in holography where there's a global symmetry. So you can keep track of okay, how do we see that? Also, we obtain that after ensemble average. After ensemble average, we get the abelian Chern-Simons theory, which has global symmetry. Then you can ask a question of, was it there before ensemble average, for example? Now, and so to describe that, let me quickly summarize what I mean by the symmetry. So this is called the zero form symmetry of the abelian Chern-Simons theory, and it's actually very simple. So I said before that everything is described by this alpha, which is the anyons, like anyon data with a topological spin, which is determined by the quadratic form. So it's a particle with a spin in a sense. And the symmetry I'm going to consider is a symmetry permuting these anyons while preserving the topological spin. And it is a kind of a symmetry because, for example, if the topological spin is preserved, in fact, the braiding with other particles also preserved. So there is no way to tell whether the replacement has happened or not by braiding with other particles, for example. So so these anyons with the same topological spin, they look similar. They look very much similar, and this permutation simply exchanges them. And it turns out that in general, for general quadratic form, there is a zoo of such symmetries. The discriminant is abelian group, but the automorphism of the abelian group can be no abelian, for example. Some dihedral group or some interesting group appears in number theory. There's a lot of number theory there. Now, you can ask the question, how is this reflected in the GDOBL formula? And after the ensemble average, it's very clear. I already said that it's a symmetry. And indeed, not surprisingly, the Eisenstein series is invariant under that symmetry. So the sigma acts on the alpha, and it's the Eisenstein series the same, which you can show immediately. But essentially because the Eisenstein series is determined from the quadratic form itself, which is preserved by the sigma. Now, you can ask the question of what happens before. It turns out that before the ensemble average, this is not the symmetry. And well, at least for generic value of this modular M, it's not the symmetry of the given CFT. But sometimes it seems to be very truly emerging. Sometimes there's a little better understanding. So that is the situation where the sigma is associated with the T-duality group. So if recall that the T-duality group acts on the modular as well, which identifies different points in the modular space, is typically quotiented out. And that if you have a T-duality group action, there is also associated, it induces the action of the anyons too. So T-duality group in general rotates the anyons. And it turns out that there is one statement, which is true, which is that if you rotate both the anyons and the modular simultaneously, and then the theta function is preserved. So this is a cross analog to what you get after ensemble average. But the important point is that it changes the value of the modular, which describes a different CFT. So it's something like a symmetry. In a sense, it's a symmetry, but it's not a symmetry of a given CFT, because a given CFT picks a particular value of M, which is not preserved by this action sigma. And well, let's see. And then you can ask the question of how does the statement above, which concerning the Eisenstein series after ensemble average, how do they arise from the statement, corresponding statement downstairs? And in fact, you can formulate it very, very generally. So suppose that you want to do the ensemble average over a parameter space M, and there's an action of the group G. I'm going to call it the ensemble symmetry because the symmetry of the modular space itself. And suppose that the action is preserved the measure over which we integrate over. So when we do the ensemble average, we're going to use that measure. And moreover, suppose that the operator we're going to ensemble average has this symmetry. that it depends on M, the moduli, as well as some other data, and such that when both of these things are permuted by sigma, and it is always preserved. So this is similar to what we had before. Now, in this case, if you assume these two things, it immediately follows that ensemble average quantity has a symmetry. So after ensemble average, M goes away. And well, okay, so here I omitted a few lines, but you can do for example, in the middle, there is a integral by M, but you can change the integral measure to M times M to sigma times M, for example, and then change the variable, etc. And then you can go to the right-hand side. And then before ensemble average, there was the M, which is transformed non-trivially. But after the ensemble average, M goes away, and the only remaining thing is alpha, which is not the parameter specified in the theory. So that becomes a global symmetry. So okay, so that's I formulated in a somewhat general way, and in fact, so it is true that in this case that there are some symmetries which acts on the ensemble itself, which we call the ensemble symmetry. And then if you have such ensemble symmetry and you do the ensemble averaging, it's kind of folded into the global symmetry. We call that the duality origami because it was the original symmetry relating different points in the moduli space, but it really is promoted to a global symmetry after ensemble average. So this is one particular mechanism where global symmetry emerges. Now, this is this is a relation between ensemble symmetry, like a T-duality, and how the global symmetry emerges. But now, let's see, now comes the little bit more extra thoughts, which is that there's let's say, so the whether global symmetry exists or not, etc., is one of the swampland conjectures. So one of the swampland conjectures is no global symmetry. But there is also another swampland conjecture called the distance conjecture. And this is also motivated partly by T-duality or duality group. So the distance conjecture says that if you go to sufficiently far in the moduli space, and they're going to get a tau of states. And the way the distance conjecture works, it turns out it's closely related with the statement that no global symmetry, because if you go far away in the distance conjecture, in the moduli space, that's typically the point where that's the Calabi-Yau becomes singular, and then that's where the non-trivial monodrome is there, and hence the non-trivial global symmetry. So the distance conjecture and then the global symmetry, no global symmetry conjecture is somewhat tied together, and one of the underlying ideas is the T-duality. So this might be a little bit too quick an explanation, but at least there are a lot of interrelation between different concepts. And since I already explained the connection to T-duality to emerging global symmetry, you can ask the question if there is something like a distance conjecture hidden in our discussion. So distance conjecture means that you have to take some moduli to infinity and extract something nice. Now, and indeed, there is some, let's say, so there is some discussion like that. So if you start with the theta function and obtain the ensemble average, there was an interesting invariant, length space invariant, which I denoted gamma before, gamma q, capital Q, comma alpha. Now, one way to extract that is simply go to the cusp. So I explained before this gamma specifies the modular transformation property and also hence the behavior at the cusps, where tau goes to some rational value. But those rational values, so those are precisely the points which are asymptotic infinity in the modular space. So you go to the infinite distance, and then you get far away, and then that's where you encounter the length space invariant. So there's a little bit of interplay between this type distance conjecture type stuff and how you get the global symmetry at the ensemble average. So, well, of course, you might wish to make this much more concrete, etc. But at least there are some statements seems to be there already. And so then you can ask the question of how can you relate it even further? For example, okay, so we don't have a complete story yet, but at least for example, one observation we had is indeed Nathan and company, they discussed the spectral decomposition. And what the statement is that ensemble average theta function gives rise to Eisenstein series. But you can try to discuss the subleading corrections. In a sense, average is average, but there are also other things, kind of like a fluctuations away from the average. And that can be discussed systematically using essentially by eigenfunction decomposition on the Laplacian. And so, and then it turns out that all these subleading corrections break the emergent global symmetry I was talking about. So, so it seems that all these things might be indicating that there is a close relation between the discussion of ensemble average we are having here, and then on the one hand, and then the question of swamp round and the global symmetries, emergent or not, etc. on the other hand. And so that's the general idea. And in fact, the even good thing is even one more comment is that our setup is like a Narain series, so it has nothing to do with string theory per se, but it turns out that in this paper by Gukov et al, they were interested in the Maxwell-Chan-Simon theory, which is the holographic average before ensemble average, actually as in the specific context of string theory compactation, ADS3 times some compact 7 manifold. So that was supposed to be capture at least some sectors of the actual string theory compactifications. So I think that's very interesting. So observation and when put together into the more modern context, it means that we have the Narain theory, which has interesting number theory structures and all that. It's also interesting when we want to consider the discussion relation between swamp round and ensemble in the context of string theory. Yeah, so it seems that sometimes there's a swamp round ideas and ensemble average is their intention, but all this seems to suggest that they should be incorporated into a single framework, which is of course string theory. Okay, I guess my time is up, so let me skip the, yeah, that's right. So, and then in fact, in the forthcoming paper, we're going to discuss, there was a global symmetry, emerging global symmetry, and you can ask the question of what happens if you gauge the global symmetries, etc. So that's going to be the content of our paper. But let's see. So, okay, so let me try to summarize. So here in this talk, we discussed ensemble averages of Narain, generalized Narain series. And these are examples of series, CF conformal field series with some non-trivial moduli space of vacua. Sorry, not the moduli space, non-trivial moduli, CFT moduli space. While it's still non-supersymmetric. So it's a non-supersymmetric CFT with a non-trivial space of marginal deformations. And hence, because of that, you can discuss the ensemble averages. And you get a beautiful formula making contact with all these Ziegler formulas and non-holomorphic Eisenstein series and all that. And the one aspect of that is everything is very precise. The precise expression is not just we are waving, hand waving, etc. But the precise expressions we can either match or not. And the holographic bulk is identified, and it's a simple Abelian-Chan-Simon series, which explains most of the ingredients. And the fascinating aspect is that this seems to be, well, kind of toy model, I thought initially, but it actually can be coming from some actual string theory. And also, it touches most of the interesting aspects of ensemble average, swap round conjecture, and of course, number theory. So I hope that we can extract even more lessons by studying these examples deeply. Thank you so much.
Hi, can I ask a question?
Yes.
Yeah, hi, Masahito. It's very nice talk. You mentioned that in the spectral decomposition, the terms that are not the average coming from integrating against the Eisenstein series cost forms, those are subleading. What are they subleading in?
Well, let's see.
Like, is there some parameter that?
Yeah, so let's see. So, well, to make that idea more precise, yeah, that's what I'm really interested in these days, and is that so I want to connect the ensemble average to infinite distance in the modular space, which is a non-trivial statement. But there are some indications that works. If that's the case, then it becomes subleading. I mean, okay, so not the infinite distance, but finite but very large distance, and then the difference from infinite, strict infinite distance, that's going to be what I mean by subleading corrections.
But I'm confused by that
Like
statement.
one over distance.
Sorry.
Yes.
In this large distance limit, the average is a very bad approximation, right? Because in the large distance limit, the gap is very, very small, whereas the average has a gap scaling with C.
Yes.
So I don't know. I'm just confused why you call it subleading, because then it seems like the quote unquote subleading terms are actually the most important.
Yeah, that's true. So in a sense, yeah. So I don't know if there's a right. So well, yes, I agree that it's not like it's really not really suppressed in that sense. So yeah. So I must say that I'm not sure if I have formulated my statement clearly enough. Yeah. I think there is a sense that well, let's see. To formulate that, I think what I'm hoping to do is to formulate that statement more precisely, I must say. But
okay,
I agree that at this point, yeah, it's a little bit of sketch of some speculation, I would say. Yes.
Yeah, thanks.
Yeah, that's right. So only substantial thing, so that I agree. So the only substantial thing, well, not substantial, but the only technical statement I made here is that this slide, I guess, saying the gamma is contained in the ensemble average. Gamma, kind of this gamma expression emerges after ensemble average of the theta functions. And that you can extract by going to the cusp, which is kind of like an infinite distance. That I think is a true statement. That's a very sharp statement. But whether you can actually interpret it as a connection between infinite distance and the ensemble average, that's a different question. Yeah. Well, yeah, in those cases, still alpha, there's only trivial alpha. Yeah, so when the Q is not self-dual, for example, okay, so usual, yeah, so usual case is the 0, 1, 1, 0, etc. But if you make it 0, k, k, 0, or something like that, and then you have a k squared, for example, k squared alpha, for example. Yes, that's right. And that relates to the fact that, yes. Index of the lattice. Well, yeah, it's some, yeah, well, yeah. That's so index. Yeah, it's a ratio of the, yeah. It's takes values in the gamma star over gamma. So yes, it's like yes. So yes. So how large the index of lambda star inside, so lambda inside lambda star. So yes. So yeah, it's related to the fact that yes, sorry, yes. Right, that's true. They didn't, and because they are not. Well, of course, they are number series, right? So they are interested in finding interesting modular transformation property. They don't. They don't have them. Yes, that's right. And then so what I'm saying is that what they did is interesting in a sense, of course, which is obviously true. They have an interesting number series structure. But maybe the only point we are adding is that it's interesting in a modern quantum field theory perspective too. It's like a Chern-Simons invariant and all the anyons and all that. So yeah. So and in fact, if you just stare at the formula, it's almost like they already knew about a lot of these things, like a CFD or anyons, etc. They didn't use the language, but all the formulas in there, and then at least they I think Jigeo knew the technical manipulation needed to understand it. So we are just adding perspective. Yes. Yes. Yeah. Yes. So yeah, I think we didn't do that much of exhaustive analysis, but the short answer is yes. So yes. So I think right. So if you go to higher genus, then the story, many of the stories are the same. So here you have a CD, etc. That becomes a matrix, and there is the action of the modular group, mapping class group, on the higher genus Riemann surface, and modular transformation determines all these things. And then you have a Hilbert space on the higher genus Riemann surface and mapping class group action, all that. And that part is the same. And then you get there's a corresponding formula. In fact, Jige also derived the same thing. I mean, Jige was very famous for Jige modular forms, so higher genus, etc. So he obviously derived the same thing for higher genus case. And then CD becomes a matrix. Yes. Yes. The short answer is yes. Yes. Yeah, although let's see. Yeah, although we haven't. Yeah, I think short answer is yes, and I know I can write it down. But but we are not too explicit in that because I thought we weren't sure whether people are interested in that, etc. But if you get the if I get the encouragement, I might be able to yeah, be more explicit. Yes, yes. Yes, 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 yes. Yeah, I mean, I'd love to. Yes. Yes, 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 that's right. See, I think that's something I wanted to know. So perhaps when I come to, yes, Cambridge, I should, yes, discuss that. But yes, the connection to that, I don't know yet. Yes. Well, of course, many similar looking things appear. So that's maybe we can use that as a path to connect. But I don't have a good comment now.